Good morning and welcome back to Calc 3. Hello everybody and welcome back to Calc 3. Hope you all are having a good Easter weekend. This is being recorded on Good Friday. It's the replacement for our Good Friday class. To start things off, an engineer, a mathematician, and a physicist were all given some amount of fence and asked to fence off the largest possible area with the smallest amount of fence, with the fence that they were given. So what do? The physicist builds a circle with his fence and says, aha, I am the most efficient. This is the most area that can be contained with this fence. The engineer says, no, I got something better. And so the engineer just builds a straight line with her fence, and then she says, we can just assume this line goes off forever in both directions. Boom, I just fenced off half the earth. Mathematician takes a little bit of fence and builds a tiny section of fence around himself. So just a tiny little bit of fence around himself and says, I'm going to declare myself to be on the outside of this fence. Therefore, everything other than this tiny enclosure is now on the inside. It's a little bit of a weird math joke. I apologize, I could have delivered that a little better. Anyways, what we're going to be doing in today's class is we are going to be looking at Standard 14. Standard which is focused on the idea of constrained optimization, which is going to be similar to the last standard of unconstrained optimization. We're going to be taking a function, we're going to be finding absolute maxima and absolute minima, except this time we're going to have a small twist to it. So here's the idea. I'm going to take a function, f of xy equals x squared plus y, which I've done here. And what I'd like to do is I'm going to find the absolute maxima and absolute minima of this function. Now you might be saying to yourselves, Dr. Gerstle, this function doesn't have any absolute maxima or minima. We're not defining it over a compact set. It keeps going up forever in this direction, down forever in that direction. And you would be right. As is, this function has no absolute extrema. But we're going to add a slight twist. And this is going to be what's called a constraint. And we'll make this process called constrained optimization. Instead of just asking, find the maxima and minima of f of xy equals x squared plus y, we're going to add a constraint and say we only care about finding maxima and minima of f of xy equals x squared plus y when we restrict ourselves to only looking at points x comma y that satisfy the equation x squared plus 2y squared is equal to 1. So in other words, we want to see how big or small this function can get when the only points that we care about are ones that satisfy this equation. So let's see what that looks like. So I'm going to graph x squared plus 2y squared equals 1. And in fact, it's going to give us a cylinder, as you can see. And so the question becomes, what are the points on the surface of f of xy, where f of xy is the original function, that also happens to intersect this cylinder? So in other words, I'm going to put little red, you might not be able to see this quite yet, but I'm putting like red boundary marks around where does the cylinder intersect the original function f. And the question becomes, if this circle-like shape is where the cylinder intersected the original function f of xy, where on this red circle shape is the function f going to have an absolute max and an absolute minimum? Dr. Gerstle doesn't look like a circle. These don't look like they connect. These are supposed to connect. There's just the CalcPlot 3D program is having trouble connecting these two pieces. But pretend like these are connected so we get a weird sort of circular-like shape. And the question is, at what points on this red shape are f of xy going to have an absolute max and an absolute min? Well, to me, it looks like we're going to have an absolute minimum at one point way down here. That f of xy is going to take on its smallest value on this red wobbly shape down here at about this point. And it looks like we're going to have an absolute maxima occur at 2 points. About right here and about right here. And so what we would like to do is to come up with a way to find the absolute maxima of the function f of this big overall surface when we're restricting ourselves to only looking at this red curve, where the original cylinder, where the constraint x squared plus 2y squared equals 1. In other words, out of all points where x squared plus 2y squared is equal to 1, where is f of xy going to be biggest, and where is f of xy going to be smallest? And to answer this question, we're going to have a new theorem and a new technique called the technique of Lagrange multipliers that's going to help us to figure this out. So let's take a look at what that looks like. So it's going to be a theorem. It's on the first page of the packet. I should have mentioned, by the way, the packet is up on Blackboard for Standard 14, which is where we're looking. So I encourage you to pull up the Standard 14 packet. You're welcome to print it out and take a look at it as we're working through this. But what that packet says, in the big theorem for this standard, is going to be, suppose that f is a function from Rn to R that is a C1 function. What does C1 mean? Well, C1 meant that f is differentiable everywhere in its domain. And all of the partial derivatives, so del f del x, del f del y, etc., are all continuous everywhere that they're defined. So we're assuming f is a C1 function from Rn to R. Given another C1 function g going from Rn to R, for some fixed scalar value c, we're going to let s be a particular set of values. S is going to be the set of all points in Rn that if we were to plug x into the function g, we're going to get the constant value c. So in other words, this is going to be the level set of g taken at some constant value c. In the example we're looking at, where the function f of xy is x squared plus y, here, the set of points where x squared plus 2y squared is equal to 1, we can think about S here as being the set of points xy such that x squared plus y squared is equal to 1, which is going to be the level set of the function g of xy equals blank at c is equal to blank. So let's think about how can we take the equation x squared plus 2y squared equals 1 and write that as a level set of some function g of xy equals some expression in terms of x and y at some value of c. Soren, what are your thoughts? Yeah, that's absolutely right, Soren. It's going to turn out to be the case that if we look at the set of all points such that if we were to plug them into the function g of xy equals x squared plus 2y squared, then the set of all points that we plugged into g of xy, this function, and get an output of 1 is going to precisely be this set S, the set of all points x comma y, such that x squared plus 2y squared is equal to 1. So we've taken our constraint equation, x squared plus 2y squared is equal to 1, and we've made it into the level set of some function. We said it's the level set of g of xy equals x squared plus 2y squared taken at c equals 1. Very good, Soren. So what is this theorem going to tell us? We have a function f from Rn to R. Well, we certainly do here. Here's our function f. F of xy is x squared plus y. We have a constraint, x squared plus 2y squared equals 1, which we can treat as being the level set of some function g from R2 to R in this case, where g of xy is x squared plus 2y squared. Our value of c, making our level set, is 1. So the constraint is just giving us the set of all points that if we plugged into g of xy, we get 1 as an output. And what the Lagrange multipliers theorem is going to tell us is that if we look at restricted to S. So this is F, vertical bar, and then S is a subscript written out, which we're going to call the restriction of F to the set S. And by that, we just mean I want to look at the function f of x, y, but the only inputs I want to look at are inputs in the set S. So in other words, I want to take the function f of x, y, but the only inputs to the function I care about are the ones in this set right here, the ones that satisfy that x squared plus 2y squared equals 1. If these are the only inputs that we care about, then on that set of points S, F has to have an absolute maxima and minima, assuming the set S is compact. And we can say something about the points where F has to have an absolute max or min on the set S. Namely, one of two things has to happen. Either the gradient of the function g, evaluated at wherever your absolute max and min are, the gradient of g has to be the 0 vector at that point, or the gradient of f evaluated at that point is going to be equal to some scalar multiple lambda times the gradient of g taken at that point. So in other words, anytime, like on that set of points we looked at on the red circle, where is f going to take on its maximum and minimum value? Well, we know at those points where it looked like we had 2 absolute max, 1 absolute min, those are all going to be points where the gradient of g is 0, g being this function here, corresponding to our constraint equation. G of xy equals x squared plus 2y squared is going to have a gradient of 0, or at those absolute maximum and minimum points, the gradient of g and the gradient of f have to be scalar multiples of each other. So let's see, who I want to pick on. So Emily, with that in mind, if we know that the restriction of f to the compact to S, if we're only looking at the points on that red circle, and we're restricting f to that circle, how can we find the absolute max and absolute min locations? What's that, Emily? Yeah, that's a good idea. What we're going to do is we can find all of the points that satisfy one of these two properties and say, well, if the absolute max and the absolute min have to occur at one of these two types of points, let's find all of these types of points, and then we can just plug them all into the function to see which is going to give us the biggest output, which of these is going to give us the smallest output. So in other words, technology is failing me. In other words, if g of xy is the function x squared plus 2y squared, and so here, this red circle, again, is where the cylinder g of x equals, where x squared plus 2y squared equals 1 intersects the function f, given by the overall surface. To find the highest and lowest points on this red circle, we need to find points where either the gradient of our function g here is 0, or where the gradient of g and the gradient of f are scalar multiples of each other. And once we find all of those two different types of points, those are going to be the potential locations for absolute maxima, i.e. these 2 points, and absolute minima, i.e. this point way down here. So let's see if we can find where these 3 points are exactly using the method of Lagrange multipliers, by finding anywhere that satisfies either condition 1 or 2, and then which ones are going to give us the biggest versus the smallest outputs. It's good. That was a good idea, Emily. I'm glad you thought of that. So what do we need to do? Let's make sure Dr. Gersel has his notes. Well, our goal is going to be to find all points x, comma, y where one of these two things happens. So we're going to start by finding all x, comma, y in R2 on S, specifically, on this set, because we only care about points satisfying x squared plus 2y squared equals 1, remember? We're going to find all xy in R2 on the set S, and I should say in the set S, where either 1, the gradient of g at that point is the 0 vector, or 2, the gradient of f at that point is a scalar multiple of the gradient of g at that point. And those are going to be our potential locations. Elizabeth, what do you think would be a good first step? We want to find every point in the set S here where the gradient of g is 0 or it's a scalar multiple of f. What do you think we should start? Find the gradient of g, find the gradient of f? Sounds pretty reasonable to me. Let's do that. So if we take the gradient of g, remember g is the function x squared plus 2y squared. Sarah, what's going to be the gradient of that function? Derivative of g with respect to x is 2x. Gradient of g with respect to y is 2y? Sure about that, Sarah? Yeah, it's not 2y, it's going to be 4y. So here we're just differentiating this function with respect to x and y. And let's see, wit. How about the gradient of f, the original function? And gradient of that one is just going to be 2x, comma, 1. Differentiate with respect to x, we get 2x. With respect to y, we get 1. So our goal is going to be to find where's the gradient of g 0, or where are these two things, vectors, scalar multiples of each other. So let's figure that out. So let's first find the points where the gradient is 0. Lori, if the gradient of g at xy is going to be the 0 vector, what can we say about x and y? Yeah, that's right, Lori. We could say that x and y both have to be 0. So 2x equals 0 is going to tell us that x is 0. 4y equals 0 is going to tell us that y is equal to 0. So 0, 0 is going to be a point. It's going to be the only point in our set S, in this set here, for where the gradient of g is going to be the 0 vector. Is everyone okay with that? Brianna, why are you shaking your head? So Brianna is going to take issue with this. She says that this is not going to be a point in the set S that where the gradient is 0. Why is that? That's right. The problem is, this is 0, 0 is going to be a point that where the gradient of g is 0, but it's not going to be a point in the set S because 0, 0 does not satisfy this equation. It's not on the level curve of g at c equals 1. It's going to be, it's going to be on the level curve at c equals 0. So we can say, but 0, 0 is not an S. So basically what that means is we don't get any points of this first type. There are no points in the set S that are going to satisfy that the gradient of any point in this set will give us 0. Nothing in the set will satisfy it. There is a point in R2, namely at the origin, where the gradient vector gives us 0 of g, but that's not a point in the set S, so we're going to discard it. So now, we need to look at the second type of point. So we need to find xy such that the gradient of g times some scalar multiple is going to be equal to the gradient of f. So let's see. So lambda can be any scalar multiple. We just need to know at what points are x, gradient of f, and gradient of g going to be scalar multiples. So we look at this equation. That's going to give us that lambda times 2x comma 4y is equal to 2x comma 1, which is the same as saying 2 lambda times x comma 4 lambda times y is equal to 2x comma 1. And we're going to need to solve a system of equations. We need that 2 lambda times x is equal to 2x, and 4 lambda times y is equal to 1. So in other words, lambda is allowed to be any real number as long as it's consistent. We need to find all values of x and y that's going to satisfy this system of equations for some value of lambda. What's that, Dr. Gersel? We have another equation, says Luke. Yeah. We also are going to need to keep in mind we only care about points in the set S. So another equation that we might want to add in is we're also going to need to still have satisfied that x squared plus 2y squared is equal to 1. But we need this in order to give us points in our set S that we care about. So let's see if we can solve this system of equations. Well, right away, I'm looking at this top equation. I think that looks pretty nice. If this equation is true, that's going to tell us that, it's right up here. It's going to tell us that 2 lambda x minus 2x is equal to 0. Jared, how can we solve this equation for lambda over x? Oh, silly me, Jared's not in class today. Jacob, how can we solve this equation? Factor it? Sounds reasonable to me. Let's factor out 2x. I'll give us 2x times lambda minus 1 is equal to 0. And 2x times lambda minus 1 is going to give us 0. Then John, what has to be true? That's right. Either x has to be 0 or lambda is 1. So we're going to have to look for two different possibilities. We're going to have to look at, first of all, the possibility where x is 0, see if we can find any values for y and lambda that'll satisfy all three of these other two equations. And we'll also look at the case where lambda equals 1 and see if lambda equals 1, are there any points that'll satisfy all of these equations. Let's start with x equals 0. So x, how can we solve one of these two equations for y if x is 0? Use the bottom equation? That's a good idea, x. I like it. We could say if x equals 0, y squared, 0 squared plus 2y squared will have to give us 1, which tells us y squared is a half, which means y is going to be plus or minus square root of 1/2. And then we can solve for what lambda would have to be using the middle equation. But it turns out we don't really care what lambda is as long as it's consistent. Lambda could be anything in the top equation. And if x is 0, this will still be true. So if x equals 0 and y is equal to plus or minus the square root of 1/2, these are going to be potential points for where we could have an absolute max or an absolute min. Because if x is 0 and y is plus or minus square root of 1/2, then the top equation will be satisfied. 0 equals 0. Bottom equation will be satisfied. The middle equation, we can find some value of lambda that'll make that work. Make lambda equal to 1 divided by 4, and then that divided by plus or minus square root of 1/2, and that'll solve it. The point is, for these 2 points, 0 comma square root of 1/2 and 0 comma negative square root of 1/2, these are going to be points where the gradient of g and the gradient of f are going to be scalar multiples of each other. You'd have to solve for lambda to find out what the scalar is, but there is some lambda that will make this vector, the gradient of f, and the gradient of g scalar multiples of each other. And so we're going to actually call these critical points of the function f restricted to s. They're critical points of where this function f, the only points we're plugging into it are points in this set S that satisfy the constraint equation. So I'm going to put a box around these, and these are going to be potential locations of absolute maxima and absolute minima of f on that set S. We have some more that we need to look at. Let's look at the possibility where lambda is equal to 1. Because if lambda equals 1, this top equation will automatically be satisfied no matter what your x is. So let's see if we can find for what values of x and y are the bottom two equations going to be satisfied if we know lambda is equal to 1. So if we plug that in, we'll get, well, let's use the second equation. I think the second equation will allow us to solve for y here pretty quickly. If 4 lambda times y, so 4 times 1 times y is equal to 1, I think that's going to tell us pretty quickly that y will have to be equal to a fourth. So if y is equal to a fourth and lambda equals 1, these top two equations will be satisfied. And to solve the third equation, we can just plug in a fourth for y and solve for x. That'll give us x squared plus 2 times a fourth squared is equal to 1. Fourth squared is 1/16 times 2 is an 8th, so that'll tell us x squared plus an 8th is equal to 1, which will tell us x squared is 7/8. So x is going to be plus or minus the square root of 7/8. And so we're going to get 2 more points that will satisfy these 3 equations, this time if lambda equals 1. That's going to be the critical points of positive square root of 7/8, comma 1/4, and negative square root of 7/8, comma 1/4. And so it turns out there are exactly 4 points on our constraint curve, on the curve S, that are going to have to satisfy that gradient of g and gradient of f are scalar multiples of each other. The 4 points are 0, comma square root of a half, 0, comma negative square root of a half, square root of 7/8, comma a fourth, negative square root of 7/8, comma 1/4. Those are going to be the 4 points on S that are going to make gradient of g and gradient of f scalar multiples of each other. I mean, there exists some lambda that will make this equation hold out true. Madeline, you wanted to ask something. Madeline was asking, how do we know that these 4 points are all points on the curve S? That's a good question, Madeline. In this case, we don't need to actually go back and check that these 4 points lie on S like we did in this case, because we use the equation x squared plus 2y squared equals 1 to find these points in the first place. Meaning, if we look here, we said x equals 0, what would y be? Well, we said, as long as y, to find what y was in this scenario, we actually plugged x equals 0 in to the constraint equation, x squared plus 2y squared equals 1. So these y values we got out of it, square root of a half, negative square root of a half, are automatically going to have to satisfy that these 2 points automatically lie on S, because we use the equation for S to find those points in the first place. And ditto with these 2 critical points, we found y equals a fourth using the lambda value, and then we plugged them back into the constraint equation, x squared plus 2y squared equals 1, to solve for x. So we already know all 4 of these points lie on S. If we didn't, we would have to check that, but we already know that. So good question. All right, we have 4 points where f restricted to S could have an absolute max or min. Looking around the room here. Sam, how can we tell which of these is going to give us an absolute max and an absolute min? That's right, Sam. Good idea. We could do the same thing we did in standard 13 and say, once we found our potential locations for absolute maxima and absolute minima, we can plug those potential locations in to the table and just say, brute force, plug all 4 of these points into the function. Whichever gives the biggest output, that's our absolute max. Whichever gives our smallest output, that's our absolute min. So let's take a look and see where that is. Okay, that's still up. Just making sure the computer didn't go to sleep on me. What the heck? Why is this not turning on? Okay, there we go. So now, we're going to plug these 4 points into a table and see what it spits out. We're going to write this back down for a second. Lambda is gradient of G is gradient of F for some lambda. So on the left, we're going to have xy. On the right, we're going to have f of xy. Whoa. Let's see. Avery, that was a good question. Why do we know we need to plug them into f and not g? Well, we already know what all 4 of these points should give us if we plug them into g of xy. It should give us 1, because specifically, all 4 of those points were chosen to be on the set S, where S is precisely the set of points that if we plug them into g of xy, we get 1 as an output. So if we plug these 4 points into g, they're all going to give the same thing, 1. So what we need to do is to plug them into f, where they're going to give different outputs. So we'll need to look at 0, comma, square root of a half, 0, comma, negative square root of a half, square root of 7/8, comma, 1/4, and negative square root of 7/8, comma, 1/4. I've plugged these into a calculator so you don't have to. The outputs they're going to give you are 1 over square root of 2, which is about 0.707. Negative 1 over square root of 2, which is about negative 0.707. 9/8, which is equal to 1.125. And 9/8 again, which is still 1.125. These have squiggly equal signs because they're approximations. These are not nice numbers. I had to cut them off after 3 decimal points. Or these are strict equalities because I didn't have to cut them off. They cut themselves off, these decimals, after 3 places. So what does that tell us? Well, once again, just like in standard 13, we can look at this list, pick out the smallest output and the largest output. Looks to me like this is going to be our smallest output, and these two are tied for our largest output. So what we can say is that f restricted to s has an absolute minimum value of -1 over square root of 2 at the point 0, comma, negative square root of a half, and an absolute maximum value of 9/8 at 2 points at plus or minus square root of 7/8, comma, 1/4. And this is going to be our final answer. That at 0, comma, negative square root of a half, we're going to get an absolute minimum value of -1 over square root of 2. And these 2 points, they're kind of tied, are going to give us the largest possible value on all of the set S for what f can give us. Meaning out of all points in the set S, these 2 points are going to give us the largest possible output when we plug them into the function f. And in fact, if we pull down the screen again for a second, we should be able to actually see that. Where here, the red circle is where is where the set S is going to intersect the graph of F. And we can actually see that these 2 points right here, these 2 black points, are at the points where x comma y is plus or minus square root of 7/8 comma 1/4, and the z value output is 9/8. And this point down here, where we look like we have an absolute minimum, is going to be at the point where x is 0 and y is negative square root of a half, giving us negative square root of a half as our output to the function. So according to our graph, it looks like we did it correctly. So what did we do? Let's see. Jack back there, kind of towards the back of the room, is looking like he'd like us to do a recap. So let's do that. We were given a function f of x, y, but instead of just being asked find f of x, absolute max and min of f of x, y, we were given a constraint equation, namely the equation x squared plus 2y squared equals 1. And we said we only want to find the absolute max and min values of f among all points satisfying this equation. Meaning if these are only inputs, how big or how small can f get? So what we did was we said, well, the points satisfying this equation right here are going to be equal to the level set of the function g of xy equals x squared plus 2y squared at c equals 1. So we said, let the x squared plus 2y squared part be a function g, and the equals 1 just means we're taking the level set at 1. We want all inputs that give the same output of 1. We then said, according to the Lagrange multipliers theorem, the points in the set S that are going to maximize or minimize f are going to have to satisfy that either the gradient of g is the 0 vector, or the gradient of g and gradient of f are scalar multiples of each other. We checked and there are no points in S satisfying that the gradient of g is 0. The only point that's going to make the gradient of g 0, 0 is at the origin, and the origin isn't in the set S. So we struck out on the first type of point, in this example at least. But when we looked for the second type of point, points in S where the gradient of g and the gradient of f were scalar multiples of each other, we basically needed to ask the question of, can we find values of x and y that'll satisfy this system of equations? Where this comes from taking the del f and del g del x, this and setting them equal to each other as scalar multiples. This equation came from setting del f del y and del g del y equal to each other, where del g del y we multiplied by a lambda again. And then this bottom equation was just the constraint equation. We found 4 solutions to this system of equations. We said if lambda is equal to 1, meaning the gradient of g and the gradient of f are equal to each other, we found a couple of points on S that would do that, namely square root of 7/8 comma 1/4 and negative square root of 7/8 comma 1/4. And we also found that if x is equal to 0, y is equal to either plus or minus square root of a half, then there's going to be some lambda. It's not going to be 1. It's going to be, well, here, we could say exactly what it is. We could say 4 lambda times plus or minus square root of a half is equal to 1. So lambda is going to be 1 divided by the quantity 4 times plus or minus square root of a half. Wasn't important, so we didn't solve for it until now. But it turns out for this value of lambda, 0 comma square root of a half and 0 comma negative square root of a half will produce points such that the gradient of f and the gradient of g are going to be scalar multiples of each other. Specifically, the gradient of g at these 2 points is going to be this lambda times the gradient of f there. And so those were all 4 points in the set S. We know they were in S because they satisfied the constraint equation. And so once we get all of these 2 types of points out of all points in S, those are going to give us all the possible locations of absolute maxima and absolute minima of the function f restricted to S. So we plugged them all into the function f using a table, found that this point gave us the smallest output, these 2 points gave us the largest output, and 0 comma square root of a half just didn't give us anything. And so at these 2 points, we got an absolute maximum for the function f restricted to s, meaning out of all the points in the little red circle on the screen, these were the 2 points that gave us the largest possible height, the largest possible output. And this point was the one that gave us the smallest possible output. And there we go. That's the method of Lagrange multipliers in a nutshell. Now, I can already hear Jack's wheels turning in his head. He's thinking, Dr. Gerstel, are you really going to make us have to do problems just from watching this one video, seeing this one example? Nah, not really. Once you get back from break, after you take the standard 13 quiz, we're going to spend another class period looking at examples of this, where you all have a chance to ask me questions before I make you do a standard 14 quiz. But this is the basic method and everything that you're going to need to know from standard 14. And when we come back, we're going to look at solving some practice problems. So don't forget, standard 13 quiz is going to be Wednesday, following the Easter break. And that'll be the next day that we meet. Hope you all are having a good Easter. And I'll see you all when you get back. Toodles.